Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for the BSc Physical Sciences students who are doing the paper on applied electronics. We have been going through a set of lectures on the chapter on quantum mechanics, and we started with Heisenberg's uncertainty principle and then moved on to the Schrodinger equation and its application to one of the most fundamental problems like particle in a box, and then we are discussing the hydrogen atom problem. And in this lecture the contents will be as follows: solution of the Schrodinger equation for the hydrogen atom, probability density, the problem of rigid rotator, objective, examples, solution to the problem. We have been seeing in the last lecture as to how Schrodinger was able to obtain the eigenvalues and eigenfunctions by solving the equation named after him, namely the Schrodinger equation. You all know by now, in the Schrodinger equation the input will be the potential. You got a potential energy part here. The outputs for any problem are the 2 quantities, namely the eigenvalue, the energy eigenvalues, and the state of the wave function that you denote by the letter psi. Psi is the so called wave function. In this problem it is the state of the electron, and to solve the Schrodinger equation to the hydrogen atom problem, what we did was to express del square, the Laplacian operator, in terms of r theta phi, the so called spherical coordinates, and then we made use of the method of separation of variables, by which we were able to split the equation into 3 equations, one containing r alone, that is the radial equation. What is r? R is the distance separating the proton and the electron, right, that is the r equation or the radial equation. The other 2 equations involve respectively theta and phi. Now, we are concentrating on the radial equation. The radial equation alone will contain E, right. E, the eigenvalues will be contained in the radial equation. It is the boundary condition that will give you the possible eigenvalues and the associated eigenfunctions. So, the important thing is the introduction of the boundary condition. We saw in the particle in a box problem how the introduction of the boundary condition automatically leads to quantization of the energy eigenvalues. Similarly, in the hydrogen atom also the introduction of the boundary condition will lead to the quantization or the discrete energies that the electron can possess in the hydrogen atom. The discrete energy levels will be coming automatically. You know, or you should be able to recall the Bohr's quantum theory, where the quantum number n was introduced through what? A postulate. You wrote mvr, or Niels Bohr wrote mvr is equal to nh bar. What is that equation? It is a postulate wherein Bohr said that the electron can revolve around a proton only in certain selected orbits, such that the angular momentum will be integral multiple of h bar. So, mvr, what is mvr? It is a angular momentum, moment of momentum, right. mv is the linear momentum, mvr should be equal to h bar. So, the quantum number n was introduced via a postulate, but here in the Schrodinger equation n will come automatically, that is what we are trying to see now. Okay. Look at the radial equation, it goes as d square r by dr square plus 2 by r into dr by r plus 2 mu, mu is the reduced mass divided by h bar square, h bar is the unit of angular momentum, multiplied by E plus Z e square, Z is the atomic number, in the case of hydrogen atom it is 1 by 4 pi epsilon naught is the permittivity, or as I told you the distance between a proton and the electron, minus L into L plus 1 by r square. L again is a quantum number, it will take only integral values, multiplied by r will be equal to 0. This is so called the radial part of the Schrodinger equation. We can't solve this straight away, but for very large r values, what should happen to psi, or what should happen to r? R is a part of psi, psi or theta phi, the wave function will be RNL of r, YLM of theta phi. It is depends upon the angular part and the radial part. So, capital R. So, the capital R should tend to what? 0 as small r goes to infinity. When small r goes to infinity, that is, you have the proton here, the probability of finding the electron cannot be increasing continuously. It should go like this, it will increase and then exponentially it should fall down, right. Otherwise, it will lead to what is called infinity catastrophe. I told you about well behaved wave function and ill behaved wave function. Supposing you write psi as e to the power of plus or minus alpha r, of the two either plus or minus, which one will you choose? So, whether you will choose psi of r as e to the power of plus alpha r, if you choose the solution e to the power of plus alpha r, it amounts to saying that the probability of finding the electron at larger and larger distances becomes larger. That is unphysical, because hydrogen atom has got a finite volume. So, the probability of finding electron should rapidly decrease after some distance. Therefore, the well behaved solution will be e to the power of minus alpha r. That is what I would like to highlight here. That is the thing to be kept in mind. The asymptotic solution is done r tending to infinity is equal to C3 into exponential of minus into square root of minus 2 mu e by h bar square into r. The detail nearer the nucleus is expanded in a power series of this form, and then this results in a series of powers of r whose coefficients must all be 0 to match the right hand side of the differential equation. From that, a recursion formula is derived for the B cube, and the requirement for the series to converge produces another quantum number n. This results in the radial solution. This is the radial solution of the Schrodinger equation. As I told you, you have R n l of R is equal to R infinity multiplied by B naught exponential of minus mu times z times e square r by 2 pi epsilon naught into h bar square multiplied by n. The important point is here you got your n is coming here, where the coefficients B naught contains the L dependence. The energy eigenvalues, without going to detailed mathematics, because unlike the case of the particle in a box, that is the first problem which we discussed with in the previous lectures, we took the first problem, or any quantum mechanical development, any quantum mechanics book, the first problem will be the particle in a box, because it does not involve higher mathematics. Here if you were to solve the Schrodinger equation, then you will come across the Legendre polynomial, logger polynomials and all. So, in order to do away with all these things, we make certain assumptions, or we assume the final expression, or we take the final result. So, the final result will come in this form: E suffix n. N is the quantum levels, the energy levels, right. N is 1 is the lowest level, 2, 3, n is 1 refers to the electron in the first orbit or the first shell, the K shell. Then n is 2 is the next shell. The important point is E n depends upon so many parameters, mu the reduced mass, that depends upon the mass of the electron and mass of the proton. The masses cannot be changed, Z cannot be changed. In an hydrogen atom is Z is 1, E is the charge of the electron, that cannot be changed. Permittivity of free space cannot be changed, the Planck's constant cannot be changed. So, all these things are constant, right. All the things that you have here, they are all constants, they can be replaced by some constant, say C. So, the whole thing E n becomes equal to minus C by what, n square. So, the important thing is the energy eigenvalue reduces to a constant divided by n square, and n, as you know, is an integer, it is a quantum number, it can take only integral values. Now, tell me what are the possible energy eigenvalues. The energy eigenvalues will be C by n square, n will be 1. So, it is C, C by 1 square is C. Then when n is 2, it is C by 2 square. So, C by 4. Then when n is 3, it is C by 9. So, these are the discrete energy eigenvalues C, C by 4, C by 9. These are the energies that the electron can assume, or the energy levels of the electrons when the electron is in the K shell, L shell, M shell, N shell and so on. Okay. Therefore, if you take an atom like sodium, you will be having electrons in the first shell, second shell and third shell and so on. You are ending up with 3 s 1. So, there will be electrons in the third shell. So, n is equal to 3 will also come into the picture. So, the discrete energy eigenvalues are given by an expression of this kind, and this should be borne in mind. I will come back to this problem again. I will ask you the question, what are the energy eigenvalues that were obtained by Schrodinger, what are the energy eigenvalues which are obtained by Niels Bohr, and what is the difference. Okay. And therefore, the energy eigenfunction is given by an expression of this kind, psi, the state of the electron, or the wave function, it refers to state of the electron. It is psi or theta phi is equal to the radial solution multiplied by the angular parts of the solution, namely theta of theta, phi of phi, that will be n times, where n is the normalization constant multiplied by R n l of R, P L m of cos theta e to the power of I of phi. This PLM of cos theta is known as the associated Legendre polynomial. Now, these things we have not discussed in detail, because as per the syllabus, or we are supposed to go through only the outline of hydrogen atom problem without going through the detailed mathematics. Therefore, you have the theta part, the phi part, and the radial part. Okay. This is the total wave function. Let us have a short break at this point. Welcome back at the break. We are trying to compare with whatever we have learnt from the Schrodinger equation with what we have already learnt from the Bohr atom model. The Bohr atom model you would have studied even in the high school, but the Schrodinger model or the quantum mechanical model of the hydrogen atom you understand only now. Look at the eigenvalue expression obtained. This is the eigenvalue expression, right. I will ask the question, here are the Schrodinger eigenvalues, right. The eigenvalues obtained from the applying the Schrodinger equation involving all this complicated mathematics, the associated Legendre polynomial, expressing del square in terms of spherical polar coordinates. You come across the Legendre polynomial and all these things, you are getting involved with higher mathematics, and finally, you are led to an equation of this kind. In what way this equation is different from the one that was obtained by Niels Bohr. You know, you have studied the Bohr atom model. In what way the expression that you obtain for the energy eigenvalues, the energy that the electron can have in the hydrogen atom is different from the Bohr atom model. The difference between the energy eigenvalues you obtain from Bohr model and the Schrodinger model. The important thing is one observes or one feels disappointed that you are arriving at the same expression that is obtained by Niels Bohr. There is no difference. This point is not very clear to many of the people. So, let me once again ask you to compare it with the one given by Niels Bohr. Niels Bohr obtained the expression for the energies of the electrons in the hydrogen atom, and after doing so much of mathematics, after using the Schrodinger equation, the quantum mechanical picture, what difference you find? You do not find any difference, right. There is no difference, nothing, there is no difference at all. What is the difference that you find? There is nothing. Then why should you undergo the trouble of spherical harmonics? You talk of YLM of theta phi, all these things, right. You have theta phi, the associated Legendre polynomial. Why should you do all these things? Now, what is the advantage of the Schrodinger equation? If you are to obtain the same eigenvalues, why should you undergo all this trouble? What is need and what is additional thing that you are getting, right, from the using the Schrodinger equation or the quantum mechanical picture? What is the additional thing that you are getting? First, it should be noted that both Bohr simplistic approach and Schrodinger's quantum mechanics give rise to the same energy eigenvalues. That is the important point. But the important difference is n, the principal quantum number, which is found in the final expression for the energy of the electron, entered into the picture, entered into the final expression via a postulate for angular momentum introduced by Bohr. Bohr said the electron should be revolving only in those orbits for which mvr should be equal to nh bar. It is a postulate. You know, postulates in physics or any subject should not be questioned, right. Postulate should not be questioned. So, n enters via a postulate, but here in quantum mechanics n comes automatically through the boundary condition. So, appearance of quantum numbers, not only n, if you go to the other the relativistic quantum mechanics, the other quantum numbers, the spin quantum number, all these things will come automatically. In quantum mechanics, the energies get automatically quantized through the introduction of boundary conditions. Hence, the boundary conditions play an important role. Now, recall this with the case of a particle in a box, right. We have already discussed the particle in a box problem. Now, what is the other significant difference between the Bohr atom model and the quantum mechanical model of the hydrogen atom? Now, what is the, why should you, because after all the eigenvalues which are obtained are the same in both cases. Then what is the significant difference between the Bohr atom model and the hydrogen atom model? Do you talk of the wave function in the hydrogen atom model, in the Bohr, according to Bohr, the Bohr atom model? You do not talk of the wave function. Do you come across the idea of wave function in the Bohr's model? Recall or remember, in the Bohr's atom model, the proton is here, the electron is considered as a particle. I will once again make the statement, the electron is considered as a particle revolving at a particular distance, namely 0.53 angstrom unit. It is at a constant distance, it is a particle, right. But according to Schrodinger quantum mechanics, the vivid orbital picture which was given by Niels Bohr is getting removed and it is replaced by a nebulous model of the electron. Electron is no longer considered as a particle, it is replaced by a cloud. What is psi? I told you in the previous lectures, psi is a thing that cannot be measured in the laboratory. What can be measured is psi star psi. What is psi star psi? It gives the probability of finding the electron at a given point. We will see some interesting pictures now. The Bohr model, you have the some usefulness for visualization, so long as it is realized that the orbits, you talk of orbit radius, but if in quantum mechanics we talk of the probabilities. Therefore, you have here what is called the probability density, right. I plot now psi star psi as a function of the distance r. What is r? That is the distance separating the proton and the electron, and according to the Bohr atom model, the electron is a particle revolving in a circular orbit having a radius 0.53 angstrom unit, right. You know what is angstrom unit, and so the electron should be found here. Okay. But according to quantum mechanics, we plot a graph connecting psi star psi and r, and you talk of the probability of finding electron, right. You do not consider the electron as a particle, it is replaced by a charge cloud, right. You got a electron is considered a charge cloud, and you talk of the probability density. What is probability density? It is psi star psi. So, the probability of finding electron is maximum here, but quantum mechanics does not rule out the possibility or a probability of finding the electron at far off places, right. Nearer the nucleus and also far away from the nucleus, the electron can be found. Therefore, whatever you have been taught in high school, that electron is a particle should be erased. You should not consider the electron always as a particle, right. The interesting thing I should point out here is quantum mechanics is not at complete variance, or is it not completely disagreeing with the Bohr atom model. Bohr said the electron should be found only at this point, it will be revolving, okay, the electron should be revolving around this as the radius, right. But according to quantum mechanics, the probability is maximum at this point, right. About 50 seconds the electron should spend its time only at this point, but for a few seconds the probability of finding the electron here is finite, here also it is finite, it becomes very small when you go to far off distances. Essentially what I am trying to tell you is the electron should not be considered as a particle, it should be treated as a charge cloud, wave like nature. It comes from the de Broglie's dual nature or the matter wave concept, if you do not assume the electron as a wave, the following things will happen, right. If the wave nature of the electron is not taken into account, you cannot explain the working of tunnel diode, right, or scanning electron microscope. You talk of X-ray diffraction. Similarly, electron diffraction. What is scanning electron diffraction? It is electron diffraction, transmission electron diffraction, transmission electron microscope. You go to any laboratory where you got the nanoscience laboratories, you got SEM, scanning electron microscope, you got transmission electron microscope, then you talk of tunnel diode, then Josephson tunneling. In very many solid state phenomena, electrons start tunneling, right. The tunneling phenomena that you come across in solids, and similarly the working of your electron microscopes cannot be explained if you assume the electron as though it is a particle. You should necessarily feel that electron is replaced by the equivalent charge cloud. This is a very important picture. This is the modern day picture of the hydrogen atom. It talks about the probability density, right. It is a quantum mechanical model of the hydrogen atom. It is a cross sectional view of the hydrogen atom. You see the electron density here, right. If you integrate the total density that you got here, that will be equal to 1. You got only one electron hydrogen atom. The total density that if you integrate, that will be equal to 1, and you see the color here is much darker. Much darker means the probability is much larger. The darker region refers to larger, higher electron density. The lower electron density, it is fading, refers to lower electron density. At a far off place from the proton, the electron density becomes smaller. That is what I show from the graph. That is what you see in this picture also. Here at some point where Niels Bohr said the electron should be revolving in orbit, at this point the probability will be maximum. So, the important message that I want to convey is electron should not be considered as a particle, it should be replaced by a charge cloud of this nature. Without this charge cloud, you will not be able to explain very many phenomena. As I told you, the functioning of electron microscopes cannot be explained, and so many other tunnel diode, so many other phenomena cannot be understood or cannot be explained. Today we may not have electron microscopes, but for the fact that electrons are treated as waves, right. Obviously, the electron densities can be measured, the electron is not a particle. Okay. Quantum mechanics also predicts that the wave function of the hydrogen atom in the ground state is symmetrical. This is the electron cloud, right. This is the nucleus is here. For higher states the electron clouds will be much more complicated, but for these electron clouds one cannot explain the very many phenomena. Then we move on to what is called the problem of rigid rotator. So far we have been talking about a proton and electron is a two body problem. Now we move on to a rigid rotator. What is a rigid rotator? A rigid rotator may be something like carbon monoxide, CO. It is a diatomic molecule, right, CO. It is a, you have got carbon here, oxygen here, two atoms, then around this axis the whole thing rotates. It is called a rigid rotator, right. Now, why should you study the rigid rotator? As we did in the case of hydrogen atom, what did we do? We found out the energies of the electrons. Similarly, here from the rigid rotator we will be finding what are called the rotational energy levels. These are the electronic energy levels that you had from the hydrogen atom problem, the energy level diagram. The rotational energy levels will be obtained by studying what is called the rigid rotator problem. So, the vibrational spectroscopy, this we will be dealing with in the lectures to come. We will move on to the summary part of this lecture, the summary goes as follows. The energy eigenvalues of hydrogen atom are obtained, the eigenfunctions which are used to calculate the probability densities were discussed. Quantum mechanical model shows that the maximum probability to find the electron is at the Bohr radius. The problem of rigid rotator is discussed. The following questions we have for this lecture, they are: write down the eigenvalues for the hydrogen atom. Is it different from the one obtained from Bohr's atom model? What additional information is obtained from the quantum mechanical model of the atom? Compare the probability density with the Bohr model. What is a rigid rotator? What is the objective of the study? With this we come to the end of this lecture. The rest of the things with regard to especially the vibrational spectroscopy and the rigid rotator we will see in the lecture to come. Thank you.